Let's try to find the area of a parabola. To be more precise, let's say that this parabola is the graph of the function y equals x squared. Each of these grid lines has a length of 1. How could we find this area right here? One thing we can do is approximate it with rectangles. These rectangles all have the same width, which I'll call dx, for a small difference in x. We can find the total area of these rectangles through a straightforward, although tedious, calculation. By decreasing dx, we can get better and better approximations for the area under the parabola. When I set dx ridiculously small, the total area seems to be 1/3. Thus, it seems that the answer is 1/3. However, this doesn't show that it is exactly 1/3. We've only shown that it is close to 1/3. To prove that the area is 1/3, we need to try something else. However, knowing that the answer should be 1/3 can help us in trying to find a better method to determine the area. So now that we know that the area should be 1/3, let's see if we can prove it. Even though we want dx to be small, let's go back to making dx a bit larger so that it is easier to see what's going on. From the equation for the parabola, for a particular value of x, we see that the area of the rectangle starting at x is x squared dx. Maybe we could find a formula for the sum of the areas of all of the rectangles. Let's think about the sum of all of the rectangles up to a certain point x and call this sum A for area. For example, if x was here, then A of x would be the sum of these rectangles. With this definition of A, the total area is simply A of 1. So if we could find some way to calculate A of x, we could find the area under the parabola. However, at this point, all we know is how to calculate the area of a single rectangle. Is there some way we could represent this area using A? Let's say x is here again. Then, as we said before, A of x is the sum of the area of these two rectangles. Unfortunately, it seems that A of x doesn't actually take the rectangle that has an area of x squared dx into account. However, if we wanted to include that rectangle, we could just increase x by dx. Then we get this point here. If we plug this value into A, we get the sum of the area of all of these rectangles. We see that A of x plus dx does include the rectangle we're interested in, although it still includes several extra rectangles. Wait a minute. If we subtract these two equations from each other, we get that the difference between these two values of A is just the area of that rectangle. And since we already know the area of this rectangle from this formula here, we can specify this equation on the bottom left purely algebraically. Thus, if we can manage to find some function that satisfies this equation, we might be able to find the total area. Let's try to guess a function that satisfies this condition. Because we know that the area should be 1/3, we can also use the fact that A of 1 is 1/3 to help us in our guessing. Some of you might be getting worried right now. Isn't this what we are trying to prove? We can't use the result of the proof in the proof, right? But that's not what we are doing. Right now, we have no idea what A might look like, and we're going to have to guess until we find it. This equation can guide us in our guessing. Thus, while guessing, I will only consider functions that are 1/3 when the input is 1. To start off simple, let's start our guessing with some monomials. We want them to be 1/3 when the input is 1, so we should divide them all by 3. We can now just calculate this difference for each function and see if we get the right thing. After quite a bit of straightforward algebra, we get these results. It seems like none of these guesses were right. I guess we'll have to make more guesses. But wait! Remember that in our final calculation, we want dx to be small. When dx is small, dx squared is even smaller, dx cubed is even smaller than that, and so on. Thus, in these equations, we can drop any terms that have dx to any power greater than or equal to 2 because they are much smaller than the other terms. Now we see that this guess right here is the correct one. Now, a lot of you probably think this last step was invalid. You can't just drop terms because you feel like it, right? It would seem that this is just another approximation similar to calculating the area with rectangles like at the beginning. But as dx gets smaller and smaller, the approximation gets closer and closer to the true value. As dx approaches 0, the approximations become exact, so we can drop these terms, meaning that this a function works as our area function. Thus, because a of 1 is 1/3, the area under the parabola is 1/3. But wait, what if another function satisfies this condition? Instead of a being x cubed over 3, let's make a be x cubed over 3 plus 1. Then using the same arguments, you can verify that this difference equation is still satisfied. So the area should be a of 1, which is equal to 4/3. It seems that this method can produce multiple different answers for the same area. So what's wrong with what we just did? The issue here is that we're missing another condition for a. Because there is no area under the parabola from 0 to 0, it must be the case that a of 0 equals 0. So this function doesn't work because a of 0 isn't 0. If you explore this method of finding areas further, here's another issue that you might run into. What we were doing was finding the area under the graph of x squared from 0 to 1. However, if we flip the graph and follow the same process, we will get that the area is negative 1/3. You can't have a negative area. The issue here is that what we have been doing is not just calculating area. The process that we developed here for calculating the area of a parabola is much more general than it might initially seem. What we are really doing here is taking a bunch of small things and integrating them together into one whole. To be precise, we are taking all of the small pieces of area x squared dx and integrating them into the area under the parabola. I'll represent this integration process with an s because it is similar to a sum. Also, we somewhat arbitrarily picked 0 and 1 as the starting and ending points, but we could have picked anything, like going from -1 to 0. We could really start and end anywhere when doing this. Thus, I'll write where we start as a subscript of the s and where we end as a superscript of the s. For historical reasons, the s is written much taller. It turns out that we can carry out this integration for more than just the parabola, or even anything graphical. If we are trying to integrate any small values that can be written in the form f of x dx, even with any bounds, we can follow the same process to find the result of this integration. We just need to find a function a satisfying these two conditions. Then by the previous argument, the result of integration is a of b. To formalize it a bit more, because we are integrating the small pieces into one whole, we will call this process integration, and the result of integration will be called an integral. It seems that this difference calculation here is more important than we initially thought, because it is involved in calculating integrals. We should give it a name as well. Let's call this the differential of the function a, because it is calculating a difference. We'll call the differential of a dA for short, and the process of finding the differential we'll call differentiation. To make integration easier, it would be useful to be able to differentiate functions quickly. Let's try to find some rules that can help us find the differential of various functions. For example, consider the sum of two functions f and g. What is the differential of this sum? Here is what the definition of the differential tells us. After expanding the sum of the functions and rearranging, we see that this part is the definition of df, and this part is the definition of dg. Thus, the differential of a sum is the sum of the differentials. But could you find a rule like this for the product of two functions? When trying to differentiate this function like we did with addition, it seems that we get stuck at this part right here. There just doesn't seem to be a way to express the result in terms of df and dg. Let's try shifting our perspective. When multiplying, it can be helpful to think of the product as an area. If the length of this line segment is f of x and the length of this line segment is g of x, then the area is equal to f of x times g of x. Now what happens when we add a small amount dx to the input? F will change by a small amount, and g will also change by a small amount. then the product of f of x plus dx and g of x plus dx is the area of this bigger rectangle. Looking at the step where we got stuck, we see that this first term is the area of the bigger rectangle and that this second term is the area of the smaller rectangle. Thus, the differential is equal to the area of this sliver. To find this area, we can divide it into 3 smaller areas. For future reference, I will call these areas A1, A2, and A3. To find these areas, we need to determine these lengths. Looking at the diagram, we see that these lengths are df and dg. At this point, we can now calculate the areas. We see that A1 is df times g, A2 is f times dg, and A3 is df times dg. However, like before, when we make these differences smaller and smaller, this last term will go to 0 much quicker than the other two, so it is insignificant. Thus, we see that the differential of a product acts according to this equation. At this point, now that we've seen the answer, it is much easier to prove it using the old method of blind calculation. Here is what the answer should be. Expanding these terms to look more like what we have here below and then distributing the product on the right, we see that there's one term that these two expressions have in common. To be able to get the FDG term in here, it would be nice if we could get this term in there as well. We could force it to go in by adding and subtracting it. We can now factor the f out, flip this subtraction, and we now have FDG. To get the correct answer, we need to find some way to get this part to be DFG. To do this, we can first factor out g of x plus dx. This part here is now df. At this point, because dx is small, we can drop it here. Either way, we know that the differential of a product is given by this equation. A natural next question is, how do you find the differential of a quotient? This looks complicated. Let's forget about looking for rules for the moment. We can't even use these rules without finding the differential of some functions first. For example, what's the differential of a constant? Well, a constant function doesn't change, so the differential is 0. What about the differential of x squared? We can think of x squared as a product, so we can use that rule for products that we found earlier. Combining these two terms, we see that the differential of x squared is 2x dx. It seems like we can keep going by continuing to use this product rule. For example, what about the differential of x cubed? We can think of x cubed as x squared times x. Applying the product rule, we get this. We've already seen that the differential of x squared is 2x dx. Simplifying a bit, we can combine these terms to see that the differential of x cubed is 3x squared dx. Wait a minute, we just stumbled upon another rule. If we keep this going, we get these results. In general, we see that the differential of x to the n is n times x to the n minus 1 dx. Wait a minute. Using this new rule, we can figure out the differential of a quotient. To do this, we need to look at the division as multiplication with the inverse of g. We can now use the product rule. Now, we can use our new power rule to differentiate g to the negative 1. Turning this back into fractions and simplifying, we get our result for the differential of a quotient. No, wait. A part of this process involved calculating the differential of g to the minus 1 using the power rule. However, when we proved the power rule, we only proved it for the case when the exponent was a positive integer. However, here we used the power rule when n was negative 1, which we know nothing about. To resolve this, we can just calculate the differential of x to the minus 1 manually. Let's write it as a fraction for now. Here is the definition of the differential. Finding common denominators and subtracting, we can now drop the x's in the numerator. Now, the dx in the denominator is insignificant, so we can get rid of it. And here we see that the power rule is in fact valid when the power is negative 1, so the quotient rule we found earlier is correct. Let's go back and summarize all that we have done. We have defined 2 new operations. The first is integration, where we take a bunch of small pieces and put them together. The second is differentiation, where we take a function and split it up into a bunch of tiny pieces that represent how the function changes. These two operations are inverses of each other. Differentiation splits a function up into small pieces, and integration puts the pieces back together. The fundamental theorem that we found is that we can calculate integrals by finding a function that differentiates to what we are integrating. This theorem is true because of the inverse relationship between differentiation and integration. At this point, it seems that we just need to find more techniques for differentiation and integration. Our foundation is pretty solid at this point, right? However, there is a problem in all that we've done, which ends up making a drastic difference in the way we do calculus. To highlight the problem, let's go back to something simple like the differential of x squared. At one point in the derivation, we had this. We have been saying that this is equal to 2x dx. We did this by saying that when dx is small, dx squared is much smaller than dx, so we can drop it. However, if we force dx to take on a particular value, say 0.001, the two expressions would not be equal. We can try to get around this by saying that dx is infinitesimal, but this just introduces a bigger issue. Infinitesimals. Are they logically sound? Do they even exist? Our problem statement had nothing to do with infinitesimals, so we shouldn't bring such a shaky foundation to our solution. However, there is another solution. Notice that every time we differentiate a function, we always get some new function times dx. Even if we think of the right-hand side as an infinitesimal, the coefficient, f prime, is just a normal function. Instead of focusing on the whole differential, we can focus just on this differential coefficient. We can do this by dividing by dx on both sides. From our original function f, we have now derived a new function, f prime. Something new that we can do with this is that we can now repeat this process. We can differentiate this new function to find a second derived function. We can keep repeating this process to get more derived functions. Derived function is a bit of a mouthful, so let's shorten it to derivative. If we could replace all uses of differentials with derivatives, then we won't be dealing with infinitesimals anymore. But an issue with this is that our intuition for everything changes drastically. Consider this function. The differential of this function represents how much the function changes as a result of a small change in input. This is what allowed us to prove our fundamental theorem, because we could integrate by seeing all the little pieces we were integrating as these small changes. However, the derivative has a completely different interpretation. The derivative is the change in the output divided by the change in the input. This is reminiscent of the rise over run formula for slope. At the point that we are looking at, we can see that this is the slope of this line. As dx gets smaller, the line approaches the line tangent to the function graph at that point. Thus, the intuitive description of the derivative is the slope of the tangent line. Now look at what happens if we forget about the differential and only use derivatives. Our fundamental theorem now says that finding the slope of a tangent line is the inverse of finding the area under the graph. What do tangent lines and areas have to do with each other? The fundamental theorem only makes sense when we think of differentiation as making tiny pieces, not tangent lines. Also, what about the product rule? In terms of derivatives, it says that tangent lines multiply according to some crazy formula. If we only teach students about derivatives, they'll get confused by this formula and will have a hard time remembering it. In terms of differentials, however, there is a simple argument for the product rule. In the end, using just the derivative is detrimental to understanding everything that we have been doing here. However, to avoid infinitesimals, we sadly have to use derivatives rather than differentials. Let's see how derivatives remove the problems we have been having. For example, let's find the derivative of x squared. Even though I am writing with the differential notation, unlike before, I will be taking dx to be an undetermined real number. We have already seen that without doing anything fancy with dx or small values, the differential is 2x dx plus dx squared. Now, we can cancel dx to just get 2x plus dx. At this point, we can set dx equal to 0. Not close to 0, not infinitesimal, but exactly 0. When we do this, we see that the derivative is 2x. We managed to do the same calculation as before, but without any of the crazy infinitesimal stuff. However, our old issue still managed to sneak in. It just did a better job at hiding itself. Let's go back to this step. We said later that dx is equal to 0. But if we set dx equal to 0 now, we see that we are dividing by 0. Thus, this method still doesn't work to remove all of the issues we had before. But maybe there's still some way to salvage this. Let's look at this situation a bit closer. To make things more concrete, let's try to calculate the derivative when x is 1. Let's take a look at this expression on its own and think of it as a function of dx, which we'll call g of dx. We already saw that we would want the derivative to be 2, so we want g of 0 to be 2. Let's graph this function. As we saw earlier, g is not defined when dx equals 0, so I've drawn a small circle at that point on the graph. But just look at that point! G practically wants to be 2 at that point. So why don't we set the value of the derivative to be the position of this hole? Of course, the question then becomes, how do we find the position of this hole? One thing we can try is to see what value the function approaches as it gets closer to the hole. Starting from this point here, as we bring it closer to the hole, we see that the output of the function gets closer and closer to 2. But this has the same problem as we had at the beginning. We can never get to 2, so how do we know that it doesn't just approach some other value close to 2, like 2.1? Well, we can at least show that it's not 2.1 by getting closer. But now what about 2.01? Once again, we can just go closer. But what about 2.001? It seems that no matter what value we pick that's greater than 2, we can get closer. However, we see that this process stops when we try to get to 2 itself. While we can get smaller and smaller by picking smaller values of dx, the limit to getting smaller is 2. But how can we formalize this notion? First, let's give a name to what we are talking about. We just described 2 as the limiting value of the function as dx got close to 0, so let's call this a limit. Currently, we have been saying that as dx approaches 0, g of dx approaches 2. Let's say then that the limit of g of dx as dx goes to 0 is 2. Let's abbreviate this with this notation. So how can we formalize what this notation means? Our first way of describing this idea was to say that as dx approaches 0, g of dx approaches 2. However, we have already seen that this is not a good definition. But recently, we saw that we can get as close to the limit as we want. Thus, we can come up with a better definition. We can make g of dx as close to 2 as we want by making dx be sufficiently close to 0. As an example, let's look back at the situation we were just looking at. If we want to get g of dx less than, say, 3, we can pick dx to be, say, 0.5. If we want to get g of dx less than 2.1, we can pick dx to be 0.05. In general, for any value greater than 2 by some amount epsilon, we can pick dx to be some value less than epsilon, such as epsilon over 2, and then g will be less than 2 plus epsilon. Thus, for any epsilon, we can find a value of dx such that g of dx is less than 2 plus epsilon. But wait, this doesn't work at all. We've lost all reference to saying that dx approaches 0. In fact, with this definition, we could say that the limit is 1, because we could then just pick values of dx close to -1 rather than 0. Really, what this shows is that this statement here is not a good formal way to describe the statement above it. We could try saying that dx needs to be close to 0 in the definition. But how would we define close? This sounds like a limit again. We can't use a limit to define a limit. Even if we can find a way around this, there's another problem with this definition. Let's consider a totally different function, the sine of 1 over x. I know the graph looks pretty crazy, but that's because as x gets close to 0, the function starts to rapidly jump back and forth between -1 and 1. So the question is, what is the limit of this function as x goes to 0? The issue here is that as x approaches 0, it keeps jumping around between 1 and -1. it seems that this function doesn't approach any value at all. Thus, I would say that the function has no limit as x approaches 0. But now look! With this definition, we can show that the limit is 0. For any epsilon, we can pick some value of x close to 0 such that f of x is less than epsilon. As I make epsilon smaller, I can bring x closer and closer to 0. Thus, this version of the definition of a limit is no good. Let's look back at our intuitive description of a limit. In our definition, we interpreted x being sufficiently close to 0 to mean that there is some x close to 0. The issue is that when we were talking about x being sufficiently close to 0, we should have been thinking about every value of x that is close to 0, not just a single value. Thus, we should change the definition to say that there is some range of values of x close to 0 such that f of x is less than epsilon. We can see now with this definition that the limit is no longer 0 because by setting epsilon to, say, 0.5, there is no range of x values near 0 such that f of x is always less than epsilon. If you want to, you can confirm that the limit isn't any other value either. With this issue dealt with, let's go back to our previous example. Remember that we were trying to say that the limit as x approaches 0 is 2. Here is the most recent iteration of our definition of what this actually means. Once again, let's try to formalize this definition a bit more. Let's look at what we are saying here graphically. For some epsilon, we have some range of x values close to 0 with f of x less than 2 plus epsilon. As we change the value of epsilon, we see that this range of x values changes as well. We can see that there is some maximum x value in this range. This maximum x value changes while epsilon changes. Let's call the distance between the hole and this maximum x value delta. We see then that in this case, the maximum x value is delta. Thus, our range of values of x are precisely those that are less than delta. This leads us to this new definition. For any epsilon, there is some delta such that for all x, if x is less than delta, then f of x is less than 2 plus epsilon. But wait, this definition doesn't mention that x approaches 0 either. That's just because we're approaching 0 and not some other number. 0 has a tendency to disappear from equations because adding 0 does nothing. Let's shift the function to the right and see what changes. Now the maximum x value is 1 plus delta rather than just delta. Thus, our definition changes to say that x will be less than 1 plus delta rather than just delta. This is where the point of approach comes in. We didn't see it earlier because it was just adding 0, which does nothing. So, is this definition a good formal description of a limit? Well, there's still a few issues with it. First, we have been saying that the function value needs to be close to 2 by saying that f of x must be less than 2 plus epsilon. However, this means that f of x could be something like negative 5,000, and this definition would still say that it's close enough to 2. That's ridiculous. However, here's a simple way to fix it. This line up here gives an upper bound on the function. All we need to do is produce a similar line to give a lower bound on the function. To make things simpler, let's say that the distance to this lower bound is also epsilon. Then the definition changes to say that f of x must also be greater than 2 minus epsilon. We can actually simplify this constraint with some algebra. You can subtract 2 everywhere to change it to this, and then this is the same thing as saying that the absolute value of f of x minus 2 is less than epsilon. This makes sense geometrically as well. The absolute value of the difference of two numbers can be interpreted as the distance between those numbers. Thus, what we are saying is that the distance between f of x and 2 must be less than epsilon, which is what the picture here shows. That solves one issue with the definition. Here's another issue. While we have been talking about x only being in this small blue region, this definition actually says that x can be anywhere in this entire region below the circle. The fix for this is simple though. We just need to say that x must be greater than 1. If x is greater than 1, then x cannot have any of the values over here on the left. But wait, Should we really be discounting all of those values? Some of those values are close to 1 as well, like these ones here. We haven't been talking about those values at all this whole time, but should we? To answer this, we need to take a step back. Remember, we have been defining limits just to define the derivative. A different function might shed some light on the issue. Let's look at the absolute value function. What is the derivative of this function at 0? We already figured out that the derivative is just the slope of the tangent line. So we can just find the tangent line and, It seems that there is no line which is the tangent line. Because of this, let's say that this function has no derivative at this point. However, look at what happens when we actually try to compute the derivative. Using a limit, the general expression for the derivative of this function is this. When x equals 0, the expression simplifies to this. Let's now graph this new function that we are taking the limit of. We've already said that there should be no limit. However, if we only look at the values to the right of 0, we see that the limit would be 1. But if we included the values to the left of 0, we would see that there is no limit. Thus, if we want limits to be able to describe derivatives, we need to look at both the right and the left of the point we are approaching, not just the right. Going back to what we had before, to include the region to the left of 1, we just need to find a second delta to be the x distance on the left. Let's call the delta on the left delta 1 and the delta on the right delta 2. Then we can change the definition to say that x must be greater than 1 minus delta 1 rather than just greater than 1. Wait, do we really need two different deltas? They look like they are the same. While they are the same in this case, in general, they are not the same. Look at this function. What is the limit as x approaches 1? Well, we can see here from the graph that the limit is 1. We can now pick some epsilon and figure out what the values of delta 1 and delta 2 have to be. To really highlight what I'm talking about, I'll pick epsilon to be 1.5. Now the valid range of x values on the left is here, so delta 1 is this big gap. On the right, the valid range of x values is here, so delta 2 is this small gap. So here we see that delta 1 is much greater than delta 2, so we need to keep track of both of them. But wait a minute, we don't actually need to find the entire x range that is between the two epsilon lines. We just need to find any x range. Thus, we can change delta 1 to be whatever we want, as long as all values of the function are still between the epsilon lines. Thus, we can set delta 1 to be equal to delta 2. At this point, we don't need to distinguish between delta 1 and delta 2 anymore. If it was delta 2 that was greater than delta 1, we could instead set delta 2 to be delta 1. This means that no matter what, we only need to find a single value of delta. Going back to our original situation again, this means that we can drop the distinction between delta 1 and delta 2. At this point, we can do the same algebraic manipulations here as we did with epsilon to see that the distance between x and 1 is less than delta. So is this definition good now? No, it isn't. What if epsilon was negative? Then the last inequality would be impossible to satisfy because the absolute value is always positive. But really, epsilon being negative is just silly. We have been interpreting epsilon as a distance from 2, so of course epsilon needs to be positive. We can fix this by saying that epsilon must be greater than 0. While we're at it, we should say that delta is positive as well because it also specifies a distance. Are there any other issues? Well, here's another one. Let's say that this function actually was defined at 1, but the value at 1 was something like 3, not 2. What would the limit be now? Well, the whole point of a limit is that we don't care about the value of the function at that point, so the limit should still be 2. However, this point is in the delta range, but it is not in the epsilon range. So according to our definition, the limit is not 2. To fix this issue, we can just say that in addition to the distance between x and 1 being less than delta, x can also not be equal to 1. This removes the point from the delta range, so the function value at that point no longer needs to be in the epsilon range. We can actually get away with making this condition slightly more concise. Saying that x is not equal to 1 is the same thing as saying that the distance between x and 1 is greater than 0. Thus, we can just say that the distance between x and 1 is greater than 0. Okay, are there any other problems with this definition? Nope, it turns out we're done. If the function had a weird domain, there's a couple extra things we would have to consider, but we don't need to worry about that here. We can finally say that the limit of f of x as x goes to 1 equals 2 is defined by this monstrous statement. We can now generalize this to any arbitrary function approaching an arbitrary point c, with the limit value being an arbitrary number L. Phew! Why did we even do this again? That's right, we were doing it to define the derivative. Given a function f, we can define the derivative with this limit. So are we finally done with all of our issues? Not remotely! We still haven't managed to define integrals or prove the fundamental theorem without infinitesimals. However, we've done enough for this video. We have pretty much covered all of the fundamental ideas of calculus, so I want to move to the conclusion. Let's give a summary of all that we've done. We started out by trying to find the area of a parabola. We explored the situation a bit, which led us to make the conjecture that the area was 1/3. We then managed to prove the conjecture, and then we realized we could generalize it to the fundamental theorem. The fundamental theorem then inspired the definition of the differential and the integral. After exploring the concept of differentials for a while, we tried to make it more rigorous. This led us to the idea of the derivative. To define the derivative, we had to develop the idea of limits. Alright, now that we've got a summary here, let's open up a calculus textbook and see the way that they do things. They start with limits. After that, they introduce derivatives. Then they describe integrals, and soon afterwards they talk about the fundamental theorem. To aid in the comparison of our development with the textbook, they do mention the area of a parabola right after this, but it's just a small example problem. So what's different between these two approaches? One obvious difference is that they do everything in basically the opposite order. Another difference is that the textbook pretty much skips these steps entirely. It is true that the textbook talked about approximating area with rectangles, but it didn't spend nearly as much time on trying to figure out how to calculate the area as we did. Instead of working their way to the fundamental theorem, they just said, here's the fundamental theorem. Now go use it to calculate integrals. There was a proof, but it didn't seem too useful in understanding why the theorem is true. Also, the textbook never even mentioned differentials. It only talked about derivatives. So what is it that caused these two methods of describing calculus to be so different? The difference is this. Even though I know this material quite well, I started from a place of purposeful ignorance. I pretended that I didn't know any of the material. That meant that we had to develop all of the ideas used in calculus ourselves without any help. We had to arrive at definitions ourselves rather than simply have them handed to us on a silver platter. We also made mistakes along the way, because making mistakes is essential to learning. You learn much more by figuring out why you were wrong than by just being right all the time. As we saw in this video, when presenting math in this way, the results can be very different than how a textbook would present the material. I am calling this method of purposeful ignorance the developmental method. We can see now why these two methods end up describing the same topic in vastly different ways. Because the textbook author knows everything already, they start with definitions. They then use the definitions to state and prove theorems, which they then use to solve problems. However, when using the developmental method, we have no knowledge, so we can't start with definitions. Instead, we start with a problem. While trying to solve this problem, we start exploring the situation surrounding the problem. During this exploration, we might find a possible solution to our problem, which we then try to prove. If the proof works out, we have a new theorem. All throughout this process, new and original concepts might pop up, and trying to formalize these concepts leads to new definitions. As we can see, the two methods have an entirely different process in presenting the material. The order of the developmental method is almost the complete opposite of the order of the textbook method. Another important difference between these two methods is that textbooks generally start with the most general case and then move to particular cases, whereas we started with particular cases and then moved to more general cases. Even though the most general case is the most useful, when developing math, you often start with specific problems before realizing that you can generalize what you are doing. In the end, there are several reasons why I think the developmental method is better than the textbook method for expository mathematical material. First, the developmental method teaches why we do math in addition to how we do math. Many people think that the math that they learned in school is useless. In reality, this is because they were never taught how to use what they learned. Second, the developmental method provides better motivation for concepts. When you first learn about limits or derivatives in a calculus course, their motivation is often not that clear. However, when using the developmental method, you only introduce them when you actually need them. Third, the developmental method is more like the math that mathematicians do. Many students think that mathematicians follow the textbook method when doing day-to-day mathematics, but mathematicians usually follow the developmental method instead. Thus, the developmental method prepares students better for the future. Fourth, by only bringing up concepts when they are needed, concepts generally make more sense when using the developmental method. Another helpful aspect of the developmental method is that it leads to more questions. I had to abruptly stop the main part of the video early because I could tell that it would just never end if I didn't stop it somewhere. The developmental method always leaves you yearning to learn more. Finally, writing mathematical material using the developmental method helps me to get into the beginner's mindset. By pretending that I don't know the material that I am teaching, I am forced to find a good explanation for what I am teaching. I am planning on using the developmental method in many of my future videos, and I would suggest using the developmental method yourself if you ever create any mathematical expositions. By doing so, I think we can help many people in their mathematical journey.